Today, we're going to introduce the concept of a buffered solution. So to do this, I want you to try to answer the following question. What is the pH of a 1.0 molar solution of HF? And the Ka value of HF is 7.2 times 10 to the minus 4. I want you to pause and see if you can work through this problem. So hopefully you remember that you need a rice table for this. And our reaction is that HF will react with water in equilibrium to make hydronium ion plus fluoride ion. And my initial concentration of HF is 1.0 molar. My initial concentrations of the two products are 0. My HF concentration is going to go down by X, and because everything's in a 1-to-1 mole ratio, these other two are going to go up by X. Now we're going to make the assumption that 1.0 minus X is going to be about equal to 1.0. Okay, and that's probably a fair assumption to make. We'll be making that assumption lots in the following unit. So just keep that in mind. Like, that's a good assumption to make. And then my equilibrium concentration of hydronium is going to be 0 plus X, so just X. And fluoride is also going to be 0 plus X, so that will also equal X. So now I can write my equilibrium expression. Notice that I'll omit water because it's a pure liquid. So now we can take that and we can say that Ka equals X squared over 1.0 molar. Okay, so this is just substituting in the X's for hydronium ion and fluoride ion, and the 1.0 molar for HF. And that gives me, so now X would equal square root of Ka, which is 7.2 times 10 to the minus 4, times that concentration of HF at equilibrium, which is 1.0, and X equals 2.683 times 10 to the minus 2 molar. Now I can find the pH of that. Negative log concentration of hydronium ion, negative log 2.683 times 10 to the minus 2, pH equals 1.57. Okay? So that's our introduction. Our buffered solution is going to start with this, where we have a weak acid, and then we're going to add something to it. So you'll notice that this problem's just a little bit different, where I have 1 molar HF solution, and then I add sodium fluoride to make a 1 molar sodium fluoride solution. So what's going to happen here? Well, we know that the HF is going to dissociate into hydronium and fluoride ion to a small extent. You're going to end up with a lot of unionized HF. Okay? So when I add the sodium fluoride, well, if I have solid sodium fluoride, it's very soluble. So that's going to make sodium ion plus fluoride ion. And you'll notice that these two, both the equilibrium and this reaction, which is not in equilibrium, generate fluoride ion. So this is something called a common ion effect, where I take something that's in equilibrium, I take a reaction in equilibrium, and I add something to it. And you remember from Le Chatelier's principle that if I do this, well, my stress is that I increase the concentration of fluoride ion, which means that the system is going to try to decrease the concentration of fluoride ion, and it'll do that by shifting towards reactants. Okay? And so when we shift towards reactants, we should use up some of that hydronium ion, and our pH should increase as that concentration of hydronium ion in solution changes. Well, let's prove it. Let's do our Rice table. So I start out with the same reaction, the same equilibrium reaction. Okay, I start out with 1.0 molar HF. I still start out with 0 hydronium ion, but I'm going to start with 1 molar fluoride ion from the sodium fluoride. And then we're going to let equilibrium establish with these conditions. Now, the only thing that has no concentration is this hydronium ion. So we can think about what would happen if, in terms of Le Chatelier's with that, we're going to try to make more hydronium ion. So this is going to increase by x, which means that this is also going to increase by x, which means that this is going to decrease by x. So this is going to be 1.0, and we're going to make that, we're going to make the assumption there. This will be x, and this will be 1.0 plus x, which we're going to make another assumption that that's just going to be 1.0. So now, when I do my my equilibrium expression, now what I get is x times the concentration of fluoride ion, which is 1, over the concentration of HF at equilibrium, which is also 1, which means that x just equals Ka, which is 7.2 times 10 to the minus 4. So the pH of this solution is 3.14, which is exactly what we thought would happen, right? We said that increasing that concentration of fluoride ion should decrease the concentration of hydronium ion at equilibrium, which it has, 7.2 times 10 to the minus 4 versus 2.683 times 10 to the minus 2, and thus decreasing the pH. Okay, so this is called a buffered solution. Okay, a buffered solution. And a buffered solution has a weak acid plus its conjugate base in high concentrations. And what that does, the whole point of a buffered solution is that they resist a change in pH.